Well, good evening, everybody. This is Dean KK4DAS, VWS Vienna Wireless Society Maker Group meeting for the 22nd of September, 2021. Thanks, everybody. Great to see everybody. Hope everybody's been making progress on their rigs and their projects. We have a special guest with us tonight, Bill Meara, N2CQR. He's going to talk to us in a few minutes. Bill has become a good friend, and you may all know him from the Solder Smoke podcast, which is kind of homebrew heaven for those of us that like to listen to people talk about homebrew radios. He's going to talk to us about kind of one of his latest projects and help bust some myths about why we use upper sideband on some bands and lower sideband on other bands, and tell us why all the experts got it wrong all those years ago. So with that, let me turn it over to Bill.
Well, thanks, Dean. All right, Dean and I were talking, and I thought it would be of interest to you guys who were building SSB transceivers to talk about an SSB transceiver that I built during the same period that you were working on yours, and I've called it the Mythbuster, and I'll explain why as we go along. First, I just want to say it's really cool what you guys have been doing. I mean, the fact that you are taking on SSB transceivers, that's a major project. Frank Harris wrote a book, and he, in his chapter on SSB transceivers, he said that SSB was the Nobel Prize of home brewing. So you guys are in Nobel Prize category here. The Solder Smoke listeners and readers have been following your exploits with a lot of interest, and I regularly include stuff about it on the blog, and we talked about it on the podcast. So hats off to all of you. Now, for tonight, what I'd like to do is talk a little bit about myth busting and what is the myth. But I don't want to beat a dead horse. I'll just go through it quickly. Then talk about something that I call spontaneous combustion construction. And I see some laughter there. You guys know what I'm talking about. You're sitting in the shack. There's a pandemic. Maybe your wife's traveling. She's gone to visit her family. You have nothing to do in the house. You start looking around. You look at all those junk boxes you got there, and the next thing you know, you're building a transceiver. Spontaneous combustion construction. That's sort of what happened with the Mythbuster. I'll talk about this later, Rig, and I say it's a little bit Yaesu, but it's quite a bit homebrew, and I'll explain that. It also evolved into what's known as an alfresco, what I call alfresco plus. I'm going to share with you some tales of woe from this project, and then talk about how if you know stuff, you can do stuff, and then we'll do some conclusions and questions. All right, first, the myth. And Dean mentioned this. This is a kind of a core question in SSB history. Why do we use LSB below 10 megahertz and USB above 10 megahertz? We've all been doing it since we've been involved in the hobby. You go on 75 and it's LSB. You go on 20, it's USB. But why? Well, I started hearing this explanation of it a long time ago. And here's the standard answer. Now, you'll hear this repeated almost endlessly by ham radio operators. A large majority of our fellow ham radio operators deeply believe this and will continue to believe it, even if you demonstrate that it's arithmetically impossible. They will still believe it. Believe me, I've tried. Here's the standard answer. Well, you see, because if you have a 9 megahertz filter and a 5.2 megahertz VFO, and by the way, that 5.2 megahertz VFO is readily available in the ARC-V command set World War II surplus transceiver. So the guys had the 5.2 megahertz VFO. You take a 9 megahertz filter. The physics of mixing will put you obviously on 75 and 20 meters. If you take the sum, you'll be on 20. If you take the difference, you'll be on 75. And here's the best part. Because of the physics of mixing, on 75, you'll be on LSB. And on 20, you'll be on USB. And because of that happy arrangement, that is why ham radio operators since the 1950s, perhaps even the 1940s, have locked into this 75-meter LSB and 20-meter USB convention. Isn't that great? I believed it for a long time. It just doesn't work. It's wrong. It can't work. And I'll briefly describe why. But it's still deeply believed. Now, the first part about how 9 and 5 will get you to 20 and 75, That's true. But the thing is, there's nothing magical that's going to allow you with one carrier oscillator frequency to magically come out on 75 LSB and 20 USB. And that's the core element of the myth. That's the element that they say explains why we are on 75 LSB and 20 USB. And it's just not true. So it sounds good, but in fact, it just doesn't work. And here, look, I just drew a little picture here. Well, first of all, I'll say this. The myth is built on a misunderstanding of a concept known as sideband inversion. For the myth to work, one of those two frequencies, either the sum or the difference frequency, has to be inverted, and one has to stay the same. That way you get on 75 LSB, but 20 USB, right? So that's a core element. For the myth to work, one has to be inverted and one not. So I always say that when you're thinking about this, you should keep in mind to keep it straight in your head, because it's hard to do. You think about this and you don't think about it for a few months. You go back and think about it again, poof, you're all messed up. Here's the way you can remember it all the time. And I call this the Hallis rule. It's from Joel Hallis, who used to work at ARRL headquarters. He taught us, and correctly taught us, that sideband inversion only occurs when, in a mixer, you subtract the signal with the modulation from the signal without the modulation. These are words to live by, my friends. Only get sideband inversion when you subtract the signal with the modulation from the signal without the modulation. Subtraction is not enough. It has to be subtraction of the signal with the modulation from the signal without the modulation, okay? So let's take what actually happens in this mythical rig. This is the rig that they claim explains the convention. You have an LSB signal generated at 9 megahertz. So you have your filter at 9 megahertz and you have everything lined up. So you got a 9 megahertz LSB signal coming out, and it's mixed with your VFO, which is running around 5.2 megahertz. So I've marked the signals with modulation in red. The 9 megahertz signal has the modulation. The 5.2 megahertz signal, that's just your VFO. You've got your LSB signal coming out at 9 megahertz. Let's look at the first case. You have 9 megahertz minus 5.2. Yep, you're on 75, 3.8. However, look, there's no sideband inversion because you're not subtracting the signal with the modulation from the signal without the modulation. You've got the reverse. No sideband inversion. So you're still on LSB. Great. Okay, so far so good. You wanted to be on LSB on 75 because that's where we started. But then look what happens on 20 meters. You're taking the 9 megahertz signal with the modulation. You're just adding it to the 5.2 megahertz signal. So obviously there's not going to be no inversion there. Come out with 14.2 megahertz, no sideband inversion. You're still on LSB, all right? So this you cannot use this kind of rig to explain why we are on 75 LSB and 20 USB, all right? So that's the myth that was busted. I got a few little charts. I'll only go through one because I don't want to beat a dead horse here, but I'll leave you the other charts so you could sort of look at them if you want to look at it from a different angle. Here's the chart I drew up this morning, busting the myth. Okay, here's the 9 megahertz signal generator, and here's what an LSB signal would look like coming out of this thing. You have 9 megahertz carrier, it's suppressed, all right? So I have a kind of a dotted line there. And then you have the audio extending down, 2.7 or 3 kcs below it. It's an LSB signal. Goes to a mixer. You mix it with your VFO, 5.2 megahertz, perhaps from your beloved ARC-5, and this is what you get. 9 megahertz with modulation minus 5.2 megahertz, you end up with 75 meter LSB. On 20 meters, you're just adding the 9 megahertz with modulation to 5.2, and you end up with 14.2. Again, LSB all the way through. The myth does not work there. Now, here's the Mythbuster. If you reverse the frequencies of the VFO and the sideband generator, then it does work, okay? But this is not the rig that they cite when they're talking about the origins of the convention. They always cite a rig like this. It's like a unicorn. It's cited a lot, but it doesn't really exist, right? Here's the one that is the correct way it works. If you have the sideband generator at 5.2 megahertz, and say you have it running on USB, you set it up, you got your filter at 5.2 megahertz, you got your carrier oscillator, boom, you got a USB signal coming out. There's the suppressed carrier at 5.2, and then extending up above it, 2.7 or 3 kcs, you have the frequencies that represent the audio USB signal. Comes to the mixer, and look what happens here. Here you're taking the 9 megahertz signal that does not have modulation, and you're subtracting from it the signal with the modulation. Now, in this case, the 5.2 megahertz has the modulation. So we go back to Hallis's rule, right? Sideband inversion occurs only when in a mixture you subtract the signal with modulation from the signal without modulation. Down here, that's exactly what's happening. The signal with modulation is being subtracted from the signal without modulation. So you get inversion. So here you take a USB signal, boom, you're on 75 LSB, my friends. That's where you want to be. Look what happens on 20. You're just taking the 9 megahertz signal from your VFO, could be from an FT101, which is the case in my rig, and you're combining it with the USB modulated signal here from your USB generator, and you end up at 14. There's no free sideband inversion here, so on 20 you're on USB. As we say on the Solder Smoke podcast, Bob is your uncle. You're in good shape. This is what you want, all right? And so when I was thinking about this, I decided to build a rig that would demonstrate that this would actually work in the second case, okay? So I'll describe now a little bit about the rig itself. But I've got a couple other diagrams here, and I'll just leave this. This talks about what goes on in the receive case. I'll leave that with you. You could take a look at it. And our fellow home brewer and my friend down in southeastern Virginia, Dino Pappas, KL0S, he wrote up a chart that describes exactly the same thing, but in his way of thinking about it. And I think with home brewing and understanding the theory, sometimes you have to draw a chart that works for you. Obviously, it has to be consistent with arithmetic and the laws of physics. It is in the case of Dino's, but it's just the way he thought about it. So he drew up this chart, and I'll leave that with you, but it demonstrates essentially the same thing. All right. Now a little bit about spontaneous construction, combustion construction. Pete was right. As he said about your projects, the radio does not build itself. In other words, you have to get in there, got to get your hands dirty, got to get some solder burns on your fingers and go in there and build it and struggle with the hardware as you've all been doing. It looks real easy. How many times do outsiders who've never done this say, oh, well, just throw in a filter and throw in a couple amplifiers and it'll be fine. That's all you have to do. You'll notice that these folks have never done it themselves. If they have, they know it's not that easy. It's hard. All right. Spontaneous combustion, I mentioned it before. I find that sometimes the needed parts and ideas seem to gather in my shack, leading to spontaneous combustion construction. And that's sort of what happened with this Mythbuster rig. Here's how the ideas and parts gathered. Now, I want to say, I too believed the myth for a while. I did. It sounds so good. It's a perfect explanation. Oh, that it was true. I believed it. About 2012, a friend of mine sent me a 9 megahertz filter, and I held that beautiful filter in my hand, and I thought I can easily make a 75 meter LSB and a 20 meter USB rig without even having to switch the carrier oscillator crystals. I could do it. And I talked about it on the podcast, how I was going to do it. And I put a post on the blog about how I was going to do it. And then a friend out in California, Steve Snortrosin Smith, set me straight. He said, that's not going to work. That's when I started to understand that the myth was a myth, that it just doesn't work. If you reverse it, it works. So now, how I got to a point where I had something where I could reverse it. During the pandemic, I built a rig called the Q31. It's a shortwave broadcast receiver. And the reason I built it, because Pete Giuliano sent me this beautiful capacitor, a variable capacitor out of a Galaxy 5 transceiver from the 1960s. But this capacitor, this variable capacitor, just was a thing of beauty. I loved it. And I built a rig. I really built the rig around the capacitor. So Pete was on the lookout for something similar. And one day he sends me an email. He says, hey, you should buy this part. It's got a great capacitor. It's got great gears. It's got anti-backlash in it. Buy it. Buy it just for the capacitor. So it's always good to follow Pete's advice. Boom, I hit the pay key and I bought what I thought was just going to be a variable capacitor. The box comes, I open it up. Yeah, the variable capacitor's there, all the gear works, everything's there, but it's attached to the VFO box of an FT101. And it is pristine. It's perfect. I flip it over. There's 3 wires coming out of it. One for the clarifier, one for the output, and one for the 6 volts in. So I tested. I put 6 volts in. I put the scope on the output. Perfect, beautiful, stable. The thing works. And I think, oh man, I got to use it. I can't just chop this thing up and use the capacitor. I got the whole VFO here, and it's the kind of circuitry I like. It's all discrete components. There's no chips in there. It's very simple circuitry, and it's really stable and really nice. So I said, that's when I started looking around for a rig to use it. And pretty quickly, this 9 megahertz VFO and a 5.2 megahertz signal SSB generator came to mind. February 2021, we're deep into the pandemic. It's cold outside. My wife buys a treadmill. Treadmill comes, the guys come and install it. It's got these 5 millimeter plywood sheets in there. They're about ready to throw it away. I said, whoa, 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 whoa. Yeah, leave the treadmill, but leave the plywood, please, too. And they looked at me like I was nuts. Nobody had asked to keep the plywood before, but I had ideas for the plywood, all right? And then finally, a little bit later in the pandemic, I'm doing my pandemic walk through the neighborhood, and somebody's thrown out a pine board sitting there on the curb. Grabbed that thing, brought it back. That became the base of the Mythbuster rig. I built it on the pine board, all right? And I'll show you here in a minute. But anyway, these are the parts and the ideas that we're kind of gathering in the shack. A little bit Yaesu. There's the part that Pete told me to buy. So in that box is the entire Yaesu FT101 VFO. It's got a reduction drive. Behind this dial, you'll see there's a couple other gears. There's anti-backlash gears. It all goes and drives a nice variable capacitor that's in there. It's a thing of beauty. A little bit Yaesu, but quite a bit homebrew, okay? So look, here's what it looks like from the top, all right? You can see here's the Yaesu VFO that I've kind of put at the center. And then I built this rig much the same way that you guys built your SSB transceivers, stage by stage. And that's a very important part. And you can see how I built it on individual boards. And as the boards got finished, I would just screw them down onto the pine board that formed the substrate. I made sure that I had a good ground plane. You'll see there's some copper tape that runs all the way down the center, and that provides a good ground plane for the whole thing. But you could see the various stages, like here's the mic amp for the mic input. Here's the audio amp output. What do I got here? Oh, here's the carrier oscillator, and here we have the balanced modulator product detector. This is a termination insensitive amplifier on one side of the crystal filter. I built a 10-pole crystal filter at 5.2 megahertz. I found some crystals on Mauser. They were like 5.242, close enough. And here's another bilateral termination insensitive amplifier here on the other end. Then I have some TR switching. Here are the bandpass filters. You guys have been talking about bandpass filters. One for 75 and one for 20. I have one double pole, double throw relay in there. Dean, when I was at this point, Dean told me, yeah, you should use 2 filters, one here and one here. But at that point, I only had 1 filter in my junk box. So I said, okay, I'm only going to use one double pole, double throw with one pole handling the input, one whole pole handling the output. I know they're too close. There's a potential for bleed over, but I tested it. It worked okay. And then down here, this whole side I left kind of reserved for RF amplifiers. So you have the first stage of RF amplification. Here you have the driver, and then it goes, here's the IRF 510 on a nice big heat sink that I actually cut a hole for and put on the outside of the box. Here's a switchable low-pass filters, one for 75, one for 20. The mixer, you can see it right in there, the ADE1, a tiny little mixer. First time I ever used one. It's kind of like an SBL1, but in a small package. It's just a diode ring with tiny little coils on both ends. It's really pretty cool. Work fine. All right, so just I'll describe some of the features, and because you guys have been involved in SSB transceiver construction, I think this is the kind of audience that would really appreciate this stuff. And believe me, there aren't too many folks out there that would. I chose a 10-pole 5.2 megahertz crystal filter because it would give me steeper skirts. You know, when you plot the bandpass of the filter on your nano VNA, sometimes they're broad skirts, sometimes they're straight up skirts. Now, we're on the air with guys who are running SDR rigs, and they take great pride in their nearly vertical skirts, right? That's why you see on the waterfall these like very, very, very vertical, signal paths showing the SSB signals. I think you could do this pretty much the same if you have enough poles in your filter. So I chose 10 poles, which is more than you usually use, to get steep skirts to make the SDR guys envious of my crystal filter signal. I use TIA amps, termination insensitive amplifiers, at both ends of the filter. This provides a stable and predictable impedance at both ends, all right, independent of what is on the other ends of the amplifiers. This is a circuit that Wes Hayward developed probably around 2009. It was used earlier in other rigs, the bidirectional filter idea, but the termination insensitive amplifier, Farhan kind of asked Wes, how do I do this? And Wes designed this termination insensitive amplifier. I talked about the 80E1 mixer. My mic amp, when came time to build the mic amp, it's a standard mic amp. So I just looked around, and the Micro-Bit-X had a nice mic amp in it using a 2N3904. So I just took what Farhan did. It worked in the Micro-Bit-X, and I just built the Micro-Bit-X mic amp and put it in there. For the balance modulator and the product detector, I used a circuit that I use a lot. Doug DeMore used it all the time. It's 2 diodes and a trifilar toroid. It's not doubly balanced, it's singly balanced, but that's all you need really in the balance modulator and the product detector, and it works real well. Key point, only one crystal used in the BFO carrier oscillator. That's the key point, because that is what the Myth promised to do. You wouldn't have to switch to 2 crystals, right? And it wouldn't work in the Myth, but it works in this one. It works in the Mythbuster. I used no RF amplifier in the receiver. And again, I was following the lead of Farhan here with the Micro-Bit-X. In Farhan's earlier Bit-X rigs, he did include RF amplification ahead of the mixer. He did it in the Bit-X 20, and he did it in the Bit-X 40 module. But when he went to the Bit-X Micro-Bit-X, he dispensed with that. And I think that's sort of the current thinking. And if you don't need an RF amplifier ahead of the mixer, you're better off without it. And I found that both on 75 and 20, I did not need it, so I didn't build it, all right? I use a cheap little LM3X36 amplifier board that you could buy on eBay. You get 10 of these things for $11. It's like a surface mount LM386, already soldered onto the board, already with the capacitors, cheap, easy. It's a bit of cheating. That's why I say quite a bit of homebrew, but heck, if I'm going to use the VFO from the Yaesu FT101, I might as well use one of these little LM386 boards, 10 of them for $11. Now, these are other boards that I just use, Sanjian frequency counters. You'll see a picture. I have 2 frequency counters on the front panel of this rig. One is set up for 20 and one is set up for 75. When I throw the band switch, the 20-meter one lights up and shows me the frequency on 20. I put the band switch down to 75. I get the same effect for that band. So it's a good way to get band indication. And then finally, an IRF 510 power amplifier with a big heat sink. Somebody sent me the heat sink. It's perfect. I could run this thing with 24 volts on the IRF 510, in which case that bigger heat sink would really be necessary. But I haven't been doing that. And I could, but I don't. Now I just have a big heat sink there. More is better than too little. So in the heat sink department. All right, here's I had a block diagram. We've already described it. This is the transmitter. Now it's bidirectional, so the receiver is very similar, but The mic amp I talked about. There's the 81. This is the two diodes, singly balanced homebrew balanced modulator, in this case carrier oscillator. TIA number 1 at about 23 dB gain goes through the 10-pole crystal filter. TIA 2 also at 23 dB gain. I measured the insertion loss here, but I don't really even remember what it was. I don't think it really matters that much because I can hear the band noise on both bands, right? I have enough gain going all the way through that when I connect that antenna on the back, boom, I can hear the band noise. The noise goes up, which means that I have enough gain in the receive system. But we're talking about the transmitter here anyway. Then it goes to the mixer, 80E1, that little chip. A friend of mine gave me one a while back. I always like to use parts that somebody gave me because it sort of adds kind of soul or personality to the rig. Then the bandpass filters with the relay, I described that before. Then 3 stages of RF amplification, the final, and then a relay that switches the low pass filters. That's the transmitter. It's very similar. It's similar to what you guys did with Pete's simple SSB rig. It's very similar also to the BitX rigs and the BitX. All the bidirectional rigs are like this. Okay. So anyway, here's what I mean by Alfresco Plus. This is what it looks like in the box. Now, the plywood is the stuff that came from the box with the treadmill, all right? Here are the 2 Sanjian frequency counters, and I've got the band switch up in the 20-meter position, so the 20-meter one lights up. If I was to put the switch down, this one, the lower one, would light up and would show a frequency on 75. In the beginning, I was just using, this is the frequency readout from the FT101. I don't even look at this thing anymore because I got these nice blue glowing numerals, glowing in Giuliano blue, by the way. Here's the main frequency dial. Yeah, this little piece of screen is another thing I found when I was walking on the walk in the afternoon. I had just cut the hole for the speaker in here, and heck, I wasn't going to stick any pencils in there, so I didn't need a screen to protect it. But I found this thing in the street. It was about the right size, brought it back, cut it out, sanded it down a little bit, painted it black. Boom. It looks pretty good, I think. Here's the audio gain control mic in. Okay. So, and again, the base is the wooden base that started out as sort of just an alfresco proof of concept kind of prototype board, but it was about the right size. And I just built this cabinet around it. The numbers mean nothing except they look kind of cool and techy. It sounds like it's a technical manual of some sort, TM something or other. Anyway, I run it off a little regulated power supply down below. All right. So tales of woe. You guys are talking about tales of woe. I'll tell you a couple things that went wrong. Now, I built each stage and tested each stage. So when you do that, everything should work when you put it together, right? Well, yeah, but it didn't in this case. The receiver always comes together first on these rigs, or usually does, and Farhan advises when you finish the receiver, stop, take a rest, and then enjoy just listening to the receiver that you built. And then go back a few days later and finish it off by building the RF amplifiers and the remaining stages in the transmitter. So that's what I did. Every time I use a relay, I put diodes across the coil of the relay, because when you snap that relay off, there's back EMF that comes up. And if you put the diode on there, that back EMF, the voltage and current goes through the diode to ground and not through your circuitry, destroying the circuitry. So I put the back EMF diodes in there, and I put capacitors, sort of a belt and suspenders. You put a 0.1 microfarad cap across there too for the same purpose. So I was being a good citizen. I was doing what I was supposed to do. But when I hooked it all together with the transmitter circuitry in there, every time I hit push to talk and put the thing in the transmit mode, it pulled an ungodly amount of current. It pulled like 5 amps through the power supply. It would blow fuses. The power supply would reduce. It was a mess. So something had gone wrong. I knew the individual circuit boards were okay, but a couple of things could have gone wrong. I could have blown the final. We blow up a lot of IRF 510s. The IRF 510 could have been conducting to ground. So I just started isolating it back. I started removing from the circuit, going back from the power amplifier, back. And then all of a sudden I went back one stage, keyed the mic, and the power draw was normal. And what it was one of these back EMF diodes that I put in there was shorted. So when I keyed it, it would pull current to ground instead of just blocking it like it was supposed to. I replaced that diode. Everything was good. And the troubleshooting was just a matter of kind of going back and isolating stages and watching for when the problem stopped. I had one other problem, one other tale of woe, and that was an intermittent loss of signal on transmit. I finished the transmitter. I took care of the first problem. I started calling CQ. I grabbed my D104. I proudly sat back, called CQ on 20 meters. And then right halfway through the CQ, I noticed that the SWR meter, the power out meter, was not jumping up anymore like it was supposed to. I was pretty much talking to myself. Then I'd click it a couple times, go back, call CQ again. Again, it would be going great. Boom, it would drop out. That's not good. That's one of the most frustrating kinds of problems because it's an intermittent problem. It'd be better if it was like that all the time, that you could just go in there and fix it. But it's intermittent. So when you go in there and try to find it, you have a tough time finding it. It's hard. So Dean and I were joking about this. With this kind of problem, one of the things you could do is just go in there and start tapping around pop, 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 while you're watching the power out and see if there's something loose. Pump, up, up. And then all of a sudden, boom, I hit it. And I could see that close by, one of the toroids that was in one of the drivers, I think it was the toroid going to the pre-driver in the RF amplifier. When I tapped it, the power would go out. When I tapped it the other way, the power would go down. So the problem was in that toroid. And I pulled the toroid out and looked at it. And the problem with these trifiller toroids is that you've scraped off the enamel so that you can make the connection. If you scrape off too much enamel, you create the possibility of a short. So some of the wires were coming in contact when it should have been just enamel to enamel coming in contact. So it was shortened to ground, and my RF wasn't getting to the amplifiers. It was just going to ground. That was the cause of the problem. So I pulled out that trifiller toroid, put in a new one, and the problem was gone. And so I was in business. So these were the only tales of woe that I had with this thing. There were far fewer problems with this rig than I had with previous SSB transceivers. I think this is the benefit of experience. As you do these things more and more, you have fewer and fewer problems. Now, they never go away. Pete will tell you, and he's told us many times about problems that he's had, and he's built almost 40 SSB transceivers. But he still will run into problems that drive him nuts. All right. It's just part of the game. And I think the best advice I heard about this is that if you get into one of these problems and you can't fix it, just leave it alone. Put the thing on the shelf for a day or two. Take a walk around the block. Do something different. Get your mind off of it. Often you'll wake up, early in the morning and think about it. And you think, wait a second. How about that? Then you'll go in and you'll see, yep, it occurred to you. You can't keep beating at it, or else you're not going to be able to come up with a solution. It's worthwhile to take a break. And I guess this gets to what Pete always says: if you know stuff, you can do stuff. And the knowledge you get from building these rigs, and being part of the International Brotherhood of Electronic Wizards and sharing information in forums like this one really, really helps. My conclusions from this whole project: the Mythbuster works great on both 75 and 20. I have many, many pleasant QSOs with it. It was fun to build and ended up with very few tales of woe. You do get better with each project complete. I consider the Myth truly busted, but here's the thing. We still don't know where the LSB USB convention comes from. I know it doesn't come from that rig that they described, that mythical rig, because it couldn't possibly work. But we still don't know where the convention came from. And there's a lot of people out there searching, and nobody can come up with a really plausible answer. The search continues. About this rig, if you guys are interested in this, I got a lot of information on the Solder Smoke blog. And as I did it, I shot little videos, 4 or 5 minute videos on each stage. There are 17 videos about the Mythbuster on the Solder Smoke YouTube channel. So, I don't know. You guys have any questions or comments? We could talk about it. I'll stop the screen. I'll leave the screen sharing up in case I want to go back.
Okay. Hey, Bill.
Yeah.
Lee, I've got a copy of the first edition of Single Sideband for the Radio Amateur from 1954.
Right.
And I was looking through this, and nowhere in there can I find anything that describes why upper sideband or lower sideband the convention.
Yeah, I know. That's one of the things
This is, this goes back to all the early QST articles.
It should be big news.
And it's not in there.
It's not in there. The first reference we see is in the second edition, the next edition, which comes out, and I think it's like 1965. There's another edition that comes out. And they have a line in there that says, over the years, there developed a vague species of convention, all right? They don't point to any decision. They don't point to any specific rig. They just say that that's something that kind of developed over the years. But how or why it developed over the years still remains a mystery. And you're right, Lee. If you go back and you study the literature, you don't see any announcement in QST saying this is the way we're going to do it. You don't see anybody saying, oh, this is the way the ITU or the FCC said we got to do it. No. It's not there. So it's also it doesn't even show up. There's no good explanation in terms of the rigs they were using, because the rigs that they were using back then all had sideband switches. So you could go on either sideband on any of the bands.
Correct.
So it's still a mystery.
So, yeah, my other comment is I think commercially everybody uses upper sideband. All maritime mobile is USB. I think all the aeronautical mobiles USB.
Yeah. You're right. And the military, Curtis LeMay went for USB early on with the Collins rigs, very early, with Strategic Air Command.
Unless you get really fancy military stuff that has independent sideband and all that stuff.
But with like the KWM2s and the S lines that LeMay got into, he told everybody to use upper sideband. Now, there's a good reason why they wanted lower sideband on 75. At the time, 75 was really the main phone band. There was some phone activity on 20. 40 was still CW only. So really, if you were a phone guy, your main interest was 75 and a bit of 20. On 75, the sideband guys liked to hang out at the very top of the band, close to 4.0, because they knew the AMers could not go up with their carriers that high, because their upper sideband would extend out of the band and they'd be getting nasty notes from the FCC. However, if you were a single sidebander, you could go right up to 3999 and use lower sideband and have all your energy below the band limit. So that's why the kind of the upper portion of 75 meters became an early hangout for sidebanders. So that is one plausible explanation for why they would want LSB on 75. But there's no real, the same logic should apply to 20, right? There's no real reason why. I haven't been able to see anybody explain why they would want to be on upper sideband on 20 when they wanted to be on lower sideband on 75. The same logic should apply to 20 meters.
Seems like you want to switch. If you're up the upper end of the band, you'd want to go lower. At the bottom CW, and you want to go upper.
Well, I mean, CW doesn't matter. You're just on one frequency. You're not worried too much about the sideband. But on sideband, it does matter because you're extending either way. And you know this when you kind of like if you're on upper sideband on 17, you got to stay away from that upper band edge, because if you think, I can go up to 18.167, sorry, you're on USB, you're going out of the band, my friend. I mean, a lot of folks don't get that, and they do it. But it makes sense on 75. It would make sense on all the bands because the phone portion is the upper portion of the band. But for some reasons that we don't understand yet, they went for upper sideband on 20 and on everything above 10 megahertz.
So a couple of months ago, Bill, I was tuning on the lower part of, on the extra part of the 40 meter band, and I was getting Donald Duck. And I'm thinking, my sideband is correct. I'm on lower sideband, and I could not tune them in. And so I switched to upper sideband, and there were a couple of guys having a conversation on upper sideband on 40 meters. It's legal. It just confused the heck out of me.
Well, maybe they were getting close to the lower band edge, and they decided to go to upper sideband to stay out of trouble. They're entirely within their rights. I used to run double sideband. When I first got into phone, I was running double sideband rigs. When I was out in the Azores, and I built double sideband rigs. They were great fun. And it was great fun because sometimes you'd get some guy come on and say, hey, old man, you're on the wrong sideband. And you'd say, no, sorry, I'm on both. You're okay. That would really blow their minds. So I ran the double sideband for a while. And then I built my first single sideband rig because I decided that it was more socially responsible to not use up twice the necessary spectrum. So I built an upper sideband rig for 17 meters. There was a community of guys that we were always talking to each other. And when I first put the upper sideband rig on, one of these guys came to me and actually said, Bill, there's something wrong with your transmitter. You've lost your lower sideband completely. And I said, hey, thank you very much, because that was the whole idea.
Bill, I've got a question for you.
Sure.
When you power your individual boards, do you run both a V plus and a ground twisted, or do you use that copper plate for your returns?
I use the copper plate. I think on many of the Bidex that I built, on 3 of the first Bidexes that I built, or 2 of the first Bidexes that I built, I used just one copper board. And so that was ground, and everything that was powered was above ground. So I guess I got into the habit of doing that, and that's the way I do it. That's why you saw that in that picture, you saw a strip of copper tape, just to make sure that all the different copper clad boards are electrically together and have a good ground plane. So I do it that way. Yeah.
Do you run your V pluses through any toroids, or just go straight from your rail to wherever it needs to be?
Each of the circuits, each of the VCC lines on each of the boards usually has some pretty serious bypassing on it. They usually have 0.1 capacitors to ground. They often have electrolytics to ground, and you're also often running it through a 10 ohm resistor before you get to the power line. So usually you don't have to think about it too much, because usually each of the circuits that you're using has incorporated quite a bit of bypassing. And when we say bypassing, we're just trying to make sure that the only thing that's on that 12 volt rail is 12 volt DC. You don't want any RF going onto that thing, because you're opening yourself up to feedback, and your amplifiers will become oscillators, and then you will be living in a tale of woe. So it's good to almost overdo it with the bypassing. And I think that is one of the kind of the bits of tribal knowledge that you learn. So all of these circuits, if you take a close look at the picture that I'll have, and you guys will get the slideshow, you'll see lots and lots of bypass capacitors on the rails, that mark the 12 volt line for each of the boards. And I went through a time where I had a lot of problems with feedback. A lot of amplifiers became oscillators. But then when I started paying more attention to bypassing, to keeping the 12 volts on those 12 volt rails really free of RF and even audio, then those problems started to appear less frequently.
If you had to come up with a standard reference architecture for us, you would do a 0.1 microfarad to ground.
Yeah, and this is I think almost everybody, when they're working in HF, uses a 0.1 microfarad to ground, usually a ceramic disc capacitor.
All right.
And then there's some disagreement about whether you should also run an kind of an electrolytic, say 100 microfarad, 200 microfarads or more to ground. Certainly in like around AF amplifiers, you see people doing that, because there's a danger of AF getting into the 12 volt supply, and then you can get audio feedback. Some people say, look, if you're putting 200 microfarads there, putting an additional 0.1 microfarad to ground is kind of pointless, but people do it. And it's a practice that has kind of developed. So I would just pay attention to whatever they have in the circuit, make sure there's enough there to prevent any of the AF or RF energy from staying on the 12 volt line.
So no wrapping your power supply wire through a toroid.
Yeah, I mean, there you're getting into kind of a choke, and that takes place. I definitely have a choke going into the power amplifier, the IRF 510. There's a choke there that goes in that keeps the RF from getting into the 12 volt circuitry. So certainly there. And I mean, I guess it depends. If you build a rig and it's working fine, and you're not seeing any problems with feedback or anything, then you really don't have to do that. However, if you start running into trouble, then you start kind of remediating by adding things like that, by putting additional chokes in there to prevent. You're just trying to break the oscillation criteria, the Barkhausen criteria that Pete always refers to prevent that circuit from providing a loop that provides for oscillation. I think that's the main problem. Sometimes you'd use additional chokes, but it depends on the circuit, depends on what particular board you're working on.
We found that in a couple of cases with our simple SSB, we've got the Arduino, we've got the SI5351, we've got the LCD, and sometimes we pick up noise from those circuits, and the noise comes in on the power line. So it was actually one of Pete's suggestions to take, kind of one by one, go through the DC feed lines and wrap a couple of turns.
Yeah. One thing I'd say about operating here in Northern Virginia, this is a very RF intense environment. There's a lot of RF here. I mean, I have a 50,000 watt FM transmitter. I can see the antenna about 2 miles from my house, and I've got an almost equally powerful AM transmitter down the other direction. So you got to be careful, because a lot of times these signals will make it into your rigs around here, and suddenly you'll hear kind of classic rock coming through your rig, and you realize that it's from the FM transmitter up the road. So, I don't use a lot of shielding. Look, I've used plywood here, so I get away with that, even in this RF intense environment. But there's a lot of shielding in the circuit itself because I'm using toroidal inductors, and those toroidal inductors are self-shielding. I use a lot of small gauge coax to interconnect, so there's not a lot of long wires that could pick up RF. I think that kind of shielding is really important. It's important to use the right kind of small RF or small coax. I get the kind that has Teflon core, 50 ohm, because if you use the stuff where the core melts, it'll melt, and then you'll have all kinds of trouble sooner or later. So it's worth it. I think it's RG316 I use as an interconnect, primarily because it's got the Teflon dielectric.
And when you do the interconnect, do you also solder the braids to ground?
Yeah, and the braids are terrible, because the braids become what we call Murphy's whiskers, right? So you cut that little piece of coax, and then right away some little pieces of braid fall out. They fall into your circuitry. They're going to short out exactly where you don't want it to. It'll mess you up. So you got to be careful to keep little pieces of braid from falling in there. But I do twist the braid. I try to solder it away from the board. That'll take care of some of the whiskers. And then I do solder the braid where I can to the copper clad board, and then keep a can of that, electronic dust off around, and just blow it in the area to make sure that you blow out any little pieces of braid that might have fallen in there. There's a kind of coax that doesn't have any braid. It just has like an external aluminum steel kind of coating that serves as like the shield. And there's no braid involved at all. I forget the RG specification, but I've used that too. And it's nice. It's harder to work with, but it gets you away from the Murphy's whiskers from the braid problem, which is a good problem to avoid. So I've used that. I don't have any of that around. I'm using RG316, and you'll see that when you look at the pictures of the Mythbuster. Let me see if I can find it here. See what I'm talking about. It's kind of hard to see. It's kind of a cream colored. Oh, you can see there's a little piece of kind of ordinary.
So I have a question. So for doing all those coax interconnects between the modules, looks like you're just soldering the coaxes right to the board versus doing SMAs or something.
I don't do it as neat as you guys. I'm really in awe of your SMA work and your connectors, and I know you have a guy who helps with that. But I think that's a good way to do it, because it makes the modules easier to connect and disconnect. But
they take up a lot of space too.
I'm sorry.
They do take up a lot of space, and it's an added complexity. So I'm on the fence.
They add work to it too. So I've just been soldering, and I've been doing that for a long time. But I think there's an advantage of having those kinds of connectors too. Now, look, there are people who are really, really kind of fanatical and kind of fanatical about shielding. So there are people that with a rig like this, they would build every single one of these stages in its own little shielded box and then have connectors on the outside. And then you connect the whole thing together and then you could be sure. But man, for me, that's just too much. I know there are stages where you're better off shielding them, and I've shielded them in different rigs, especially around VFOs and things like that. But it adds a lot of work, and it makes it a lot more difficult to service. This, with everything above the board, it's very easy to service. You don't have to flip over any boards. In the old days, when we used to etch and solder on the bottom and have the parts on the top and then solder traces down below, man, that was a pain because every time you worked on the board, you'd have to flip it over, flip it back, flip it over. You did that 4 or 5 times, the wires would break, the coax would break. Ugh, it was terrible. I kind of like this. This is all Manhattan construction, by the way. These are all little pads that are glued to the top of PC boards, all right? So there's nothing, there's no etched. You'll if you look closely at the boards, you'll see where I cut out little squares of PC board and super glued it to the board. So this whole rig is built with Manhattan construction techniques. And that's my main technique. I've done printed boards and everything else, but I do it with the Manhattan construction technique. And for me, it works. It's simple, it's fast, and it's easy to work on. I could go in there and pull a part off and put a new one on in a minute. Whereas if it was a kind of a printed circuit board, remove the board, solder it out from underneath, worry about lifting the pads, worrying about breaking the leads. For me, this works better.
Hey, Bill, since you're on the picture, when we were started building our simple sideband transceivers, Pete really discouraged us from trying to build an IF filter. You just kind of said, I bought all these crystals and built my IF filter. You kind of just went through it like it was no big deal. So is it really no big deal? Because Pete kind of discouraged us. He said it would be a big deal to try to build a good one.
I mean, Pete and I have differences of opinion on different things. Like, for example, he's a big fan of the SI5351. He does not like analog VFOs. He's made that very clear. And what you just mentioned is another area where he's a believer in kind of factory-made crystal filters. I like these kind of crystal filters. Now, it's hard to do. It's harder to do it this way. It's more perilous. You might end up not getting it to work exactly the way you want, but you get better at it over time. The trick is you have to, when you buy these crystals from, say, Mauser, 5.247 megahertz, Mauser doesn't give you all the parameters that you need. You need to determine the motional inductance and the motional capacitance of the CM and the LM. The degree to which that quartz crystal also acts as an inductor and a capacitor. You have to measure the plate capacitance. You have to determine the equivalent series resistance and the Q of the particular crystal. Then you go to some software, you plug in all that data. And usually I use some software from AADE. There's a number of other crystal design software packages out there. You plug in the data, and then you start telling it, okay, I want to use 10 of these crystals. I want to use it in a cone topography, and I want to match it at either end to 50 ohms. And then it will spit out a circuit with the passband that you called for with those particular crystals and tell you how to match the impedance that exists at the endpoints of the filter with the 50 ohms that you want to go into your TIA amps. And then it'll actually tell you how to construct a matching network to match them. So you'll see in this one, you'll see I have two little toroids here on either side. Those are impedance matching transformers that take what is the characteristic impedance of the filter and match it to the 50 ohms that works best into the TIA amps. I would say it's possible to do. I mean, I've built many of these things, and I'm no wizard. I'm not an engineer or anything like that. It's all just ham stuff. But you could do it. A lot of people do it. I wouldn't be deterred. It's rewarding. It's difficult. You have to do some measurement, and then you have to make sure that what you've built actually conforms in terms of passband and kind of filter shape to what you want. But it's an opportunity to use your your nano VNA, and Dean has done this quite a bit, where he looks at a filter, sweeps it, takes a look and see what it looks like. It's probably cheaper than using store-bought crystals or store-bought filters, but I think it adds another element of homebrew to it. I mean, my feeling is you should try to build as much of this stuff as possible, and that makes it more and more of a truly homebrew rig. This one is, for me, quite a bit far from pure home brewing. I mean, because I'm using a VFO from a Yaesu FT101. Right. This is like dealing with the devil here. I mean, come on. And I've got a board over here with a surface mount LM386. I hang my head in shame. I mean, but you've already done that other stuff before, so you can do it. That's what I tell myself. That's what I tell myself, Mike. So, thank you for saying that. No, I know. I do that too. So you can do it. How hard is it to measure those parameters on those crystals? So it's not hard. There's a method called the G3UUR method. You build a little device, and all you really do is you switch in 30 picofarads, and you measure the frequency before, you measure the frequency after that. From that, you can calculate the CM and the LM. And then there's a way that Chuck Adams has developed to determine the equivalent series resistance in the Q. Once you have those numbers, and then the plate capacitance, you just measure the capacitance across the terminals. Once you get those numbers, then you go to some of the software. There's Dishal software out there, where you plug these parameters in, tell them how wide you want the crystal, how wide you want the filter, how many elements are you using, and it'll spit out a schematic saying, okay, build this. Then you build it, then you measure it, and it might be a little bit off. And then you start tweaking and you get it to where you want it. But it's satisfying, and I'm really pleased with this filter. I wanted it tight, so it is tight. It's not hi-fi. It's not broad. It's at about 2.5, 2.6 kilohertz wide, and the skirts are SDR steep. Oh, that's good. Ours was 2.4, I think, Dean, at 2.8. Yep. So, yeah, I mean, you guys going a lot broader now, but I don't think it's necessary. I think it's well, that explains it, because you kind of blew through that just like it was. Oh, no big deal. I built an IF filter, so it's a lot more behind the scenes.
I looked at that test circuit, and Bill, for the first time homebrewer, that test circuit is as complicated as our entire. No. But you're looking at W1FB's crystal tester. Yeah, and I had the same reaction. That's not what I'm talking about. The G3UUR circuit. Just check it out. Just do a Google search on G3UUR crystal circuit. I mean, look, I have one floating around here. It's just a little board. It's a switch that switches in 30 picofarads. And then you measure the oscillation. Oh yeah, crystal parameter circuit. Yeah.
So you also can do it with a spectrum analyzer and a tracking generator, which is what I did.
Yeah.
I have a little test fixture. I put my crystal in, and then substitute a little 100 ohm variable resistor to get the series resistance, and it's not that hard. I bought like 100 crystals for $10.
Yeah,
off eBay, and I went through and measured them all and sorted them out. So I got all the approximately correct, series resonant frequencies were all about the same. And then I was able to use the Dishal software, and I built some filters.
Yeah, you could do it. There's a lot of different ways to do it, depending on what kind of gear you have. But the G3UUR method and Chuck Adams, and then you go to the software, and you kind of go back and forth between the software and then what you built, and you measure it, and you test it, and everything else. Yeah. And so, for example, I built it the first time, and I found it was a bit too narrow. So I changed the series capacitors. I bought some additional capacitors. I think I lowered them in capacitance, and that caused the filter to broaden out a bit. Now, one thing to know that if you look at when you sweep your fish crystal and you see that the pass band is jagged, that indicates that you've got bad matches at both sides. All right. If you're not providing the kind of impedance that the filter wants to see at both ends, then you will get a jagged pass band. Whereas if you get a nice smooth flat pass band, you've got it properly matched. So these are the kind of tricks and things, the problems that you learn to look for, and you realize, okay, my passband's jagged. It's probably, I have a bad match at either end. I got to work on that a little bit. Or it's too tight. Maybe I'm using crystals, bypass capacitors to ground that are too high. I need to lower them a bit, broaden it out a bit. I went through a couple different iterations with this. That's why you can see the soldering around the crystals. The board's a little bit messed up because I soldered parts in and then took them out and then soldered different parts in.
Bill, do you have a closer in picture of that filter?
I don't, but I have a whole video. If you go to the YouTube channel, you'll see a video on the construction. I think it's the first this was the first stage I built, the first thing I built in this one. And I did a whole video with I think better pictures on it there.
Cool.
Did you ground all your cases, Bill?
I did not. I know guys usually do that. I never have. And it didn't seem to make any difference.
Yeah, it's interesting. So we went through a whole process when we were kind of getting ready to do this because the filters we were going to use were from the GQRP club and they ran out of them.
I remember that. Yeah.
We had to do a search and we got a guy in the UK that built filters, but he looks like he basically did what you did to build the filters. I mean, his filters look, they look virtually identical.
Yeah.
And but I went through the same process with Pete. I said, well, why don't we just build them? I said, it's just one more circuit. And he's like, no, you don't want to do that. He says, you got enough, you got enough problems already.
but he might have been thinking that you're dealing with a group of folks who haven't built a rig like this before.
That's exactly right.
And in that case, I mean, it is better to avoid problems. And later on, you could, then do it. You having put together a whole rig and got it working together with the commercial filter, sure. And then later on, go and try to roll your own. In this case, it was good because I would have a tough time finding a commercial filter at 5.2 megahertz, right? But I wanted a filter at 5.2 because I wanted to sort of prove this Mythbuster concept. Mauser had the crystals at 5.247. I bought like 20 of them and I knew I would use 10. I've got 10 of them sitting in the bag over there. I could probably build another 5.2 megahertz crystal filter if I wanted to.
Yeah, what I found was some of the extra crystals is what I use for my LO oscillator.
Yeah, well, that's it. One of them is down here. One of those additional crystals is down here, and it's the carrier oscillator and the BFO. I picked one that happened to be a little bit in the direction where I needed it, and then I put some I think a coil and capacitor in there to move it to exactly where I needed it. Now, as you guys have found out with your rig, when you're setting it up, the placement of that carrier oscillator or BFO in relation to the passband of the filter is critical. This is what determines whether the rig sounds good or not. A lot of times you'll hear guys who are, fooling around with BitX rigs. They'll say, oh man, I built it and it just sounds terrible. It sounds awful. And then you ask them, well, how much attention did you pay to the placement of the carrier oscillator frequency in relation to the passband of the filter? And you find out that they figured that whatever came out of the box was okay. They didn't spend a lot of time on it. Whereas if you do that, it'll pay off a lot. Now, when I was building my first sideband rigs, I didn't have a whole lot of test gear. And I actually had I was in the Azores and I had a friend in Sweden, SM4FQW. And we were talking and I said to him, listen, I need to adjust my carrier oscillator frequency and I need you to listen from Sweden and tell me when I get it right. And he said, okay. And I got my little screwdriver with the trimmer cap and I would call SM4FQW. How's this sound? Terrible. How's this sound? Better. How's this sound? Better. How's this sound? Worse. Go back. And we did that a few times. And that's how I adjusted the location. Now, believe me, there are better ways to do this. But I mean, that's essentially what I was doing. I was moving the carrier oscillator in relation to the unmovable passband of that crystal filter.
So guys, for us, we do that with the Arduino. So we set that's done in the sketch. But the important thing for us is to make sure that you got the center frequency of the filter plugged into that sketch so that when you do those offsets, they actually work the way they're supposed to.
That's right. Yeah.
So that's the other thing. Pete definitely has an aversion to analog VFOs, because I told him, the next thing we're going to do is this this direct conversion. And I said, I think we'll do a VFO. He's like, why would you want to do that? Just use the SI5351. Well, one of my points was, hey, Pete, I haven't built 50 transceivers, and I've actually never built a VFO. So it might be a new interesting learning for me.
It is fun. It's not. He's right. There's it has its ups and downs. It's a bit hit and miss. But when I built my BitX20 transceiver, I wanted to build it completely analog, completely chip free. So I built a VFO in there, and that's a VFO. Now a halfway house that you could do, and when you're getting started, and this is something that Doug DeMore always recommended, was a VXO. All right, get a crystal, and then use a coil and a cap in series with the crystal to move it. So you're building an analog variable frequency oscillator, but there's a crystal there that prevents things from getting too far out of control. Now you can't move it too far, and I think it's like you could move it like 10% or something like that. Either way, maybe more. But I have one. I'm using one on 17 meters right now. I have my oscillator is a crystal oscillator at 23 megahertz. The IF is at 5 megahertz, right? So subtraction gets you down into the 18 megahertz range. But I have two crystals in there, and with those two crystals, I can cover the entire 17 meter phone band. And it's an interesting way to go.
Switch one of them in at the top end and another end at the bottom end.
Yeah, and I have a panel switch on the front, and I just throw it. I'm throwing it right now as I'm talking to you. And when I notice that I can see on the little Sanjian readout where I am, and I want to go down a little bit lower, I throw it in one direction, and there I am. But it's an easy way to do it. Doug DeMore really recommended it, and he said it's especially useful if you're building a rig that's going to be for portable operation, where you're going to be out in the cold or the heat or something like that. You have a VXO in there, so it might be something to look at. One thing I'd advise is, if you're going to do the VXO, get the crystal as high as possible in frequency. So that way, I started out with this rig, the crystals were at 12 megahertz. I couldn't move them that much. So then I went up and I used at 23 megahertz, I could move them a lot more. Of course, you got into the sideband inversion problem in one way or another, but that was a different story. Yeah.
So my comment about the better capacitors is go look for old surplus stuff, like ARC-V radios. They have really nice worm gear-driven vacuum variables. And just variable capacitors in them.
I'm guiltily, I have a fondness for the capacitors out of the Heathkit QF1Q multiplier. And I have destroyed several of these fine pieces of vintage radio equipment.
I think if you want, like, say a 9 megahertz VFO, then something like the ones of these variable caps of an ARC-V would cover like 9 to 9.5 easy.
Yeah. But if you got the ARC-V, if you get that thing working, the whole VFO is worth keeping right there. That ARC-V VFO, that was what people were using back in the day. And if you get one that's a complete junker, you can pull the capacitors out of it. But you might end up like I am with this thing, where you go to buy the capacitor and you end up keeping the whole VFO.
Yeah. Well, there's the circuit to use. I think people claim the stablest VFOs are what, VACers, VACKER.
Yeah, the VACer VFO, that was good. Then you get the series tune claps. There's a whole bunch of different circuits. But Pete, one of the things that Pete hates about these kind of VFOs is that depending on the capacitor and depending on the circuit, if you get it up at one end, the frequency gets kind of squished together, and a small movement results in a big frequency change. But it is possible, as is the case in this VFO, where you have a fairly linear dial readout. That's not a problem.
The other really odd thing is, I haven't tried this, is if you want a really stable one, long-term stability, use a vacuum tube instead of a transistor, like a 6CW4 Navistor. And the reason is transistor characteristics drift with temperature. Tubes do not.
Yeah. Well, I mean, these are other tricks. I mean, I think if you just, ironically, if you leave the transistor out of the box, leave all the heat producing active components out of the box and just let them just sort of vent their heat and let the heat dissipate, things stabilize quite a bit. And I've got the VFOs that I've built with transistors have ended up being really, really stable. I mean, there might be, when you first turn them on, when things are getting hot, they might drift a little bit, but then they'll stabilize. And then you've got some pretty stable VFOs. I mean, it's not SI 5351 stable, but if you could live with, 10 hertz drift during the first 15 minutes, if you can get past that, for me, I like it better that way.
They should be actually quieter, right?
7.201 exactly. If you're not on 7.201 exactly, the frequency police are going to come get you.
I know. They're very cruel on 40 meters. Cruel.
Yeah, but they should have lower
frequency.
Yeah, but you should have lower phase noise.
Yeah.
Which is one of the issues with all the digital based.
Bill, just a quick one. Are you happy with the audio chain going out to your speaker?
Yes, I am. And I this is something that I kind of learned or relearned from my building of the Q31. In the Q31, I had one stage of audio amplification from I think a single BJT or an FET. I'm not sure. I don't remember. But then it went right to an LM386. And a lot of people complain about the LM386. I think it produces superb, high quality, high volume. I got more audio than I need. And there's so much audio gain in this thing that I don't really have to worry too much about IF gain or insertion loss in the filter or anything like that, because you only need about 100, 110 dB from the antenna to the speaker. And I got more than enough. I'm running this thing with the speaker, the volume control, nowhere near the top. So I think it's fine. I mean, I like the LM386. I don't generally like chips, but I like the LM386 because it's a simple op amp. And if you want to, you can understand how everything works in there. There's no digital magic or lines of code or 3 billion transistors inside a black box that you'll never understand. It's simple enough to get your head around, and which makes it kind of more acceptable for me. But yeah, I like the 3LM386. I know there are better amplifiers, but man, that little board, if you look on eBay, 10 of those boards for $11. I mean, I'll be building a lot of rigs with these little AF.
So speaking of the LM386 and your audio, Dean thankfully put an AGC circuit in here, because I've noticed, you really have to ride the volume knob. I mean, do you have any kind of AGC built into yours?
I followed Farhan on this. Farhan, from the beginning, from the BitX 20s on, he just would say, I don't put AGC in this. I don't think it's necessary. I think it's a frill. You could turn the gain control down if you want. And I have over time been tempted occasionally to try to put AGC in my rigs. I never have. I may do it one day, because I recognize that it helps with the ability to handle large signals. It helps with the dynamic range of the receiver.
Right.
But it adds a level of complexity that I don't think it's really necessary. So I'm sticking with Farhan on this one. When he goes AGC, I'll go AGC with him.
It only takes 2 transistors, Bill.
Or an op amp. Talk to Dean about
or an op amp and a FET. I use it.
And for that reason, I never have any S meters in these rigs, because the S meters are usually derived from the AGC. So people will tell me, hey, am I S6 or am I S7 right now? And I'll just look and I'll say, well, I think you're S7, old man. You're doing real fine.
Well, we had a problem with the simple 40s, because we have so much. I know that the 3 transistors we have up there driving the fourth audio transistor, by the time we get out of that, strong signals, we're actually clipping our 386s. We got so much audio.
Yeah.
This thing,
I think that's one. I don't know whether you guys have an RF amplifier ahead of the mixer. I don't know.
Yeah, I was wondering. You mentioned that earlier. That might be part of our problem because we do have an RF amplifier going into the first mixer.
Or the other thing we may have need to do is maybe we should put a switchable attenuator in.
Switchable attenuator is great. That's better. It's almost like it's almost the equivalent of an RF gain control you could have in there. Some guys even build, they're able to turn down the IF gain, RF gain, IF gain, and AF gain. That might be overkill, but a switchable attenuator would be good. But I never really experienced clipping with this thing, and I think part of that is that there was really no need for RF amplification ahead of the mixer.
Well, and you don't have we also have an amplifier, a transistor, a 3904 or 6 in front of that. So I've often wondered if we couldn't just remove that and just use the 386 by itself.
Yeah, I think a lot of times people like the transistor before it because it kind of reduces the noise. Usually see an LM386 or another op amp with a single discrete transistor ahead of it. I think that's for that establishes the noise parameters there.
And again, you're feeding the output of the mixer, so you maybe not want to put the mixer directly into the high impedance.
Yeah, that's probably another reason. The other thing that you do here is from pin 1 to 8, that sets the gain. Mm-hmm. And if you put a 10 microfarad cap across 10 to 8, that greatly increases the gain. If you remove the cap, it greatly reduces the gain of the LM386. What I did with this one is when I put 10 microfarads there, it was way too much gain. When I had 0 microfarads in there, it was way too little gain. So I think I found a 5 microfarad cap halfway. And even though it's surface mount, I went in and soldered that cap across pins 1 and 8 and kind of tailored the gain from that LM386. So looking at pins 1 and 8 on an LM386, you could move the gain of that op amp around quite a bit. That's something you might want to look at.
Yeah, we do. I clipped it off, and I still get too much gain in that audio amp.
Yeah,
I think Mike, you probably are the same, and Dean. Yeah.
I have it on, but now that I have the agency in there, it works.
Oh, okay, yeah, because I couldn't. Yeah, it was driving me nuts. I clipped it off, and now it's sort of okay.
And maybe even play around with the pot that you have going in there, the pot input. You might need to just put some more resistance in there, so it has to go through more resistance before it gets to the LM386. You're just changing basically the range of your AF gain control. I don't know. These are kind of fun projects. This is great. You guys are getting into it.
That's what I was just going to say. This is kind of the point of the kind of the beauty of Pete's design with all these little modules is like, you don't like this audio stage, do whatever you want, build your own, right?
I don't know if you guys realize how rare this kind of conversation is among hams. This is probably one of the only groups in the United States right now that's doing this, if not the world. It's just not happening a lot. And it used to happen at every club meeting every week in every radio club across the country. There were groups of people that were interested in this technical stuff at this level. So I think it's terrific. And I am going to rejoin VWS for like the 5th time, just so that I could be part of this group. I think it's going to be great. I first joined back in '92, so I'm an old timer. Hey, it's been great. Thanks very much for inviting me, Dean, and thanks to everybody.
Thanks, Bill. Thanks so much for sharing.
Check out the Solder Smoke blog and the links at the end. You'll see them there, and I think that might give a lot more detail on each one of these little boards. But I really enjoyed talking to you guys, and hope we can continue.
Thanks, everybody. We're going to close out the meeting. Bill, thanks so much. I have your slides. They haven't changed since you sent them to me, right? So
no, they have. I'll send you an updated version.
Oh, send me the updated one, and then I'll pop them up on our share drive for the guys, and I will send you a link to the video as soon as it's ready.
All right, I'll send you the slides right now, Dean. Good night, guys. Thanks very much.
Super. Good night, everybody.
Good night, Dean. Good night, everybody.
Good night.